Okay, so we're going to look at some graphs of polynomials today, which, quick recap, if you're finding a polynomial of least degree with those three zeros, then you can write your factors that go along with it. So zeros of 2 and 3 would give you x minus 2 and x minus 3, and 0 of negative 1 would give you x plus 1. That'd be your least degree polynomial, each of those factors to the first power. So some things that we talked about in Algebra 2, graphs of polynomials. It's easier to talk about if you have one to look at as we go along here. So let's say we're looking at 2x to the third plus 6x squared plus 1 as our polynomial. So the degree of your polynomial corresponds to how many zeros it has. So if that's a degree 3 polynomial, it's going to have 3 zeros. Some of them might be complex and some of them might be real numbers. So there's at most 3 real zeros, which means when we graph it, there's going to be at most 3 X-intercepts. So degree matches your number of zeros, so at most 3 real zeros for a degree 3 polynomial. And your number of X-intercepts on your graph is going to be at most 3. Your degree is also related to your end behavior. If it's an odd degree polynomial, your ends will both point different directions, one up, one down. Versus an even degree polynomial, both ends are going to go the same direction. But what happens in the middle is you're going to have what are called some turning points, where it switches from like going up to coming back down or down to back up. And the number of turning points is at most 1 fewer than the degree of your polynomial. So if you have a degree 3 polynomial, its graph can have at most 2 turning points. And like I said a second ago, your end behavior is related to your degree. So if your polynomial is even degree, like x to the 4th, 2x to the 6th, something where your highest degree term has an even exponent, your ends are going to go the same direction. So as x approaches negative infinity, the left side of your graph, and as x approaches positive infinity on the right side, both of your ends are going to have the same behavior, either both up or both down. It's related to your leading coefficient, whether they both point up or both point down. Positive leading coefficient, they're both going to point up. Negative leading coefficient, they're both going to point down. Odd degree, the ends are going to go opposite directions, so one up, one down. And again, kind of which one's which is related to your leading coefficient. So if you have like a polynomial, it's like x to the third or 2x to the fifth, both ends are going to go opposite ways. Positive leading coefficient, it's going to rise as you go towards the right. A negative leading coefficient, it's going to fall as you go towards the right. Which if you think about what you know about lines, like line that was just y equals 2x would go up with a positive slope and down if it was y equals negative 2x. So it's kind of got that same behavior if that helps you remember which one's which. Okay, we're going to use what we talked about to do a little matching of some polynomials with their graphs. So I would narrow this down kind of based on degree first. So if you look at graphs 1 and 2, those ones are going to be even degree polynomials because both of their ends are going the same direction. So if you look at your options for our polynomials that we have, the ones that are even degree would be B and C. Then if you take a look at your leading coefficients, B has a negative leading coefficient, so both ends should be pointing down, and C has a positive leading coefficient, so both ends should be pointing up. So we can do some matching. Graph 1 has to be polynomial B, and graph 2 has to be polynomial C. The ones that are left have odd degree, so all 3 of the remaining graphs are odd degree polynomials. There's kind of an odd one out. Graph 5 rises as you go towards the right, so it's going to have a positive leading coefficient as opposed to the other 2. So anytime you're looking at a graph, odd degree, it's rising up as you go towards the right, you're looking for a positive leading coefficient on your polynomial. If you look at our options, E is kind of out of order, but its highest degree term is 1x to the 5th, which would be a positive leading coefficient. So graph 5 is going to match polynomial e there. The last two look pretty similar. They're both negative leading coefficients and odd degree. If you look at their y-intercepts though, one crosses at 0, 0, and the other one's down at like y equals negative 50. So if you look at your remaining polynomials and think about plugging in 0 for x to see where it's going to cross your y-axis at, if you plug 0 in for x on A, you're going to have that graph pass through the point 0, 0. If you plug 0 in for x on your other polynomial D, you're going to get negative 50. So matching those points to the appropriate graphs, A is going to have to be graph 3 because it goes through 0, 0, and D is going to have to be graph 4 because it has a y-intercept of negative 50. Okay, so we're going to answer a few more questions actually regarding those graphs. So part A, which of the graphs above cannot be the graph of a cubic polynomial? So cubic polynomial would be degree 3. So using what we know about degree 3 polynomials, we know that if it's an odd degree, both ends have to go opposite directions, which means it can't be graphs 1 or 2, because those are even degree. The graphs 3, 4, and 5 are all odd degree, but if you think about the number of turning points, if this is a cubic polynomial, there can be at most 2 turning points. And if you look at like graphs 3 and 4, those have 2 turning points, so they could be cubic. But graph 5 has forward turning points, which means this can't be graph 5. Graph 5 is going to have to be a higher degree odd polynomial. Can't be degree 3. It's got too many turning points. Okay, so B says how many real zeros for graph 1. If you come up to graph 1, your zeros that are real numbers are going to correspond to your x-intercepts. So there are 2 real zeros for graph number 1 because we have 2 x-intercepts. There could be some non-real complex zeros. Can't tell those just from the graph though. And part C, we're supposed to use the graph of this polynomial, which actually we match that to graph 5. If you come up and look at its graph, we're supposed to use that to factor our polynomial f of x. So you can use your x-intercepts to start with some initial factors. So if you go up to graph 5 and look at your x-intercepts, you can get some factors. We've got x-intercepts of negative 3, 0, and 2. So let's start with a polynomial that has factors of x plus 3, x, and x minus 2 to correspond with our zeros. Since this is a degree 5 polynomial, some of those factors have to have multiplicities other than 1. The 2 x-intercepts of negative 3 and 0, since your graph just like touches the x-axis there, those factors actually have to have even multiplicities to get that shape. So they have to have multiplicities of like 2 or 4 versus the 0 of 2, where it just crosses all the way through the x-axis, has to have an odd multiplicity. So if we think about the fact that our polynomial is degree 5, our factors of x and x plus 3 actually have to be squared because they do have to have that behavior where they just touch the x-axis there. I can't go higher because otherwise the degree of the whole polynomial would be greater than 5. Okay, so I made a mistake and had to fix it, so ignore kind of my writing down below till I fixed it. Okay, there we go. So if you plug in 1 for your x's, we're supposed to get 16 out for your y, negative 16 out for your y's. So solve for a. You get a is equal to 1, so your final polynomial is right there. We're going to sketch some graphs just so you kind of get the general idea of how to create a graph of a polynomial based on what we've talked about so far. They're not going to be perfect, but we're just trying to get you to make some connections between the equations and your graph shape. I would start with your x-intercepts. So if you set the polynomial equal to 0 and solve, you should figure out what x values you're going to have as your x-intercepts. So on this one, we're going to end up with 3 different x-intercepts. So one's going to be at, if you solve all these, -2, one's going to be at 3, and one's going to be at 0. So plot your x-intercepts to start with on your x-axis. Didn't give myself a scale here, so let me do that real quick. Okay. Then if you think about your end behavior, if you were to multiply this back out times all of the factors together, you could see what your highest degree term is. That's the one that would influence your end behavior. But I want to save myself some work, so I'm just going to think about it. If I multiplied 2x times x times x, everything that has a variable in it back together, that's going to be my leading term that's going to define the end behavior of my graph. None of the other terms actually affect what the ends are going to do. So it's an odd degree polynomial, positive leading coefficient. It's going to rise up as I go towards the right. So I'm going to go ahead and draw those ends in, up on the right side, down on the left side. Now I'm going to plug in some additional points between my x-intercepts. So between each pair of x-intercepts, so like between 0 and -2, I need to know if I'm above or below my x-axis. Same thing between the x values of 1 and 3. So let's plug in -1 to be in between those 2 x-intercepts there. And let's plug in +1 to be check on the right-hand side and see if I'm above or below. So if you plug -1 in for your x values in your original polynomial, you end up with 8. And if you plug +1 in, you get -12. Plotting those points, they're going to be approximate. So right about there, we'll say, I'm just going to label it instead of making a scale on my y-axis. And then at 1, I'm down below the x-axis at -12. Those aren't necessarily the maximum and minimum values of my graph, but I do know that my graph's going to go through it, and we are just going for a general shape. So if I draw it in through my x-intercepts and those points, my graph shape looks something like that. So that's the main idea. X-intercepts, end behavior, some additional points. Let's do another one, and I'll show you actually how you can save yourselves a little bit of work. So x-intercepts, again, set your polynomial equal to 0 and solve. End behavior, if you think about multiplying all of your highest degree terms together, you'd have x squared times x squared would give you x to the 5th. So your ends are going to look exactly like on the last graph. Left end down, right end up. All right. I could plug in some additional points, but actually I'm going to talk multiplicity for how to do this instead. So if I go ahead and graph my x-intercepts and my ends, and then think about my factors that I have in my original and the multiplicities of each one, instead of making this XY chart, which you could do if you want to, if you look at your factors of like x squared and x plus 3, those factors have even multiplicities. So you're going to have your graph just like touch the x-axis at -3 and at 0. It's not going to cross it there. So you could draw that in. And then it's going to actually cross it at 2. Which means your graph's going to end up looking something like I sketched right there. So you could plug in x values in between your x-intercepts and also find that you're below the x-axis, or you could just use your even multiplicity to realize it's just going to touch the x-axis at 0 and -3. All right, one more. We can do this. This one, though, is not factored, so we're going to have to factor it first before we can graph it. So throwback to a couple days ago, we're going to have to guess what we think some potential zeros might be by taking our factors of 8 divided by factors of 1, because rational zeros theorem says that any of those could be zeros of this polynomial. So we're going to do a little bit of guessing here until we find a 0, and then use that to write our polynomial in factored form. So I cheated and looked at my notes from last year. So I'm going to go ahead and guess, in quotation marks, that 1 is a 0 of this polynomial. So let's do some division and make sure that x minus 1 does divide in evenly. It does. So you can rewrite that original polynomial in factored form of x minus 1 times x squared plus 6x plus 8. And then that's actually to the point where we can just factor it further without having to divide again, because x squared plus 6x plus 8 factors into x plus 2 times x plus 4. All right, so we did the work and we wrote it in factored form. Now we know our x-intercepts, again, are going to be 1, -2, and -4, which we will plot on our graph. Thank goodness Notability can make straight lines. So plotting our x-intercepts. All right, done. Okay, well, it's degree 3. My ends are gonna go, I really should have mixed it up, I guess. My ends are again gonna go down on the left and up on the right. And then my multiplicity of all those factors is 1, so it's gonna cross at every single one. I'm gonna use that instead of plugging in x values. My final graph should look like that. All right, good luck on your assignment.